Hello, calculus fans, and welcome to section 3.9, where we cover related rates. Now, related rates are one of those sections that typically cause a lot of problems for a calculus student. There's probably three sections that a Calc 1 student will struggle with the most. One of them is epsilon delta proofs, which are not really covered as much anymore. I used to cover those when I first started teaching, but I haven't covered them for a few years now. The other one is our current section, related rates, and the third is optimization problems, which we'll see later in chapter 4. So for some of you, this will be a bit of a challenging section. So I'm going to give you kind of an overview of how you can handle these problems. And just be aware, though, it's going to be somewhat of a tricky section. You're going to have to be a little bit stubborn and persistent and just keep on working at these problems to get the hang of it. And they definitely take a little bit of practice. So the general idea is this. The idea is to compute the rate of change of one quantity in terms of the rate of change of another quantity, which may be more easily measured. To do this, we find an equation that relates the two quantities and then use the chain rule to differentiate both sides with respect to time. So we're going to differentiate with respect to time. And we'll do this with implicit differentiation. So we'll be doing some implicit differentiation on these problems. So we'll start off with kind of an easier problem. Example 1 says a circle is increasing in area at a rate of 16 pi square inches per second. How fast is the radius increasing when the radius is 2 inches? So I'm going to give this like this 6-step process that should work on all of these. It'll at least give us a framework, so we at least have like a starting point, have something to go off. So whenever I start these, I always think of step 1, just get a picture. So I'm just going to draw a picture every time. Now, in a case like this, there's not really much to show. We've just got a circle. But I'll just draw a picture of a circle and then fill in any details. But in this case, there's not much. Again, this is kind of a simple process, but I'll just draw a picture anyway. I'm still going to do the 6 steps just so we can sort of get used to this idea. So we got the circle. It says how fast is radius increasing when the radius is 2 inches. I know this is not the greatest circle ever. But okay, so we've got radius of 2 inches. So step 1, we draw a picture. Step 2, I always look for the rate we know. They're going to give us some rate of change typically. So let's look for the rate we know. Step 2. So in this case, it tells us that the circle is increasing in area at the rate of 16 pi square inches per second. And when we think of this rate, the rate we know, I'm going to write it in Leibniz notation. So I'm going to think of it so it says it's increasing in area. So I'm going to think of it as the change in area with respect to time. And I'm purposely going to use this as opposed to just saying like A prime. I'm going to write it this way because when we write it this way, although this is kind of a bulkier way to do it, with related rates, this notation will make it easier for us to keep track of everything. So this is dA dt, so we know what variables we're talking about. And it tells us that this is 16 pi square inches per second. So that's the rate we know. Step 3, I always look for the rate we want. There's going to be some rate typically that they ask us about. The rate we want. Okay. The rate we want is from right here. It says, how fast is the radius increasing when the radius is 2 inches? So we can write this like this. Again, with Leibniz notation, we can say, we'll say dr dt. This is the rate of change of the radius with respect to time. And then it says when the radius is 2. So the way we do this with Leibniz notation, we do this line and we say r equals 2. So whereas with a different notation, maybe we'd say r prime of 2. that'd be maybe something we're more familiar with. But with Leibniz notation, we do a line here and say the rate of change of r with respect to t when r equals 2 in the vertical line is how we show that. Again, it's kind of bulky, but for what we're doing, it's going to work better. Okay, so we've got the picture, rate we know, the rate we want. The fourth thing we want to write down is we want to find an equation. So step 4, we want an equation relating blank and blank. And these blanks are whatever these variables are from step 2 and 3. So we've got the area and the radius. Okay, so we want to find an equation relating the area and the radius. And this will usually be something that has to do with our picture. So in this case, you've got a circle. So we basically want to find an equation that has to do with a circle that has both the area and the radius. And with a circle, of course, probably what you'll think of is area equals pi r squared. So whenever we get to step 4 on one of these problems, look at these variables here. Think of the geometry of the picture. It'll usually be something that has to do with the geometry of our picture involving these variables, whatever they are. So in this case, you got a circle, and probably the thing that you would think of is area equals pi r squared. Okay, so that is step 4. For step 5, we look back at this equation, and then we differentiate with respect to t. So with respect to t, and you'll notice there are no variables, there's no t variables here, so we're going to have to do implicit differentiation. So we'll differentiate this side, so we'll get dA dt, and over here, we have pi r squared, so r is the variable, pi is just a constant. So when we differentiate, we're going to get dA dt equals, here we're going to need the power rule because r is our variable, so we'll get 2 pi r. So we get 2 pi r, but r is not t. So once again, we have the chain rule, or we have implicit differentiation, right? dr dt. So this implicit differentiation will happen all the time in this section because we're differentiating with respect to t. A is a variable and it's not t. R is a variable and it's not t. So we'll have that all the time. So if like there were a t here, differentiate with respect to t, we just get 1. But these are both variables that are not t, so we're going to have this implicit differentiation, right? So a prime, when you differentiate this way, a prime looks like dA dt, right, with Leibniz notation. And then same thing over here. So that's the thing to keep in mind with this section. We're going to have this implicit differentiation all the time because this variable that we differentiate with respect to is time, t, and these typically will not have the variable t. Okay, so once step 5 is done, the final step, step 6, once we have this, step 6, we substitute known values and solve. So substitute known values and solve. So what we're talking about is this. The values that we know here, we solve. So we had earlier, if I look at this from what we had up here, dA dt is 16 pi, right? Square inches per second. So I'm going to put 16 pi here, 2 pi r, dr dt. Well, we're looking for dr dt, but we're looking for it at the point where r equals 2. So I'm going to plug in a 2 for r. Okay, so once we do that, what we'll get is 16 pi equals 2 pi times 2 dr dt. So you get 16 pi equals 4 pi dr dt. So of course we divide both sides by 4 pi. That'll cancel, and we'll get dr dt equals 4. Now here's where it's this notation is really nice for units of measure. So dr dt is 4, right? 16 pi divided by 4 pi is 4. But then the units, you want to write the units down. Well, the units are going to be the units of r over the units of t. So the units of r are inches, and the units of t for time is seconds. So the final answer is dr dt equals 4 inches per second. Okay, let's take a look at example 2. Example 2, we've got a 25-foot ladder leaning against the wall and sliding toward the floor, which is very bad if you're on the ladder. It says that the foot of the ladder is sliding away from the base of the wall at the rate of 15 feet per second. How fast is the tip of the ladder sliding down the wall when the top of the ladder is 7 feet from the ground? Now, after reading this, you'll probably see why I think it's always a good idea to just draw a picture. So for step 1, let's just draw a picture of this so we can get a feel for what's actually happening. Okay, so we've got this wall here, we've got the ground, a right angle, 25-foot ladder, and it says the foot of the ladder is sliding away from the base of the wall at the rate of 15 feet per second. So as this thing is falling down, so the ladder's falling here, this here is sliding away from the wall, so it's sliding in this direction at the rate of 15 feet per second. So I'm just going to label this to make it a little easier to deal with. So I'll call this distance here x, and this distance here y, just to give us something to make it a little easier to deal with. And of course, this is a 25-foot ladder here. And it tells us that the ladder is sliding away from the base of the wall. So this point here is sliding over here. And it tells us it's a rate of 15 feet per second. So if this is x, I'm just going to write this right here, part of the picture, just to make it a little easier. That means that dx dt is 15 feet per second. Right? This x is changing with respect to time at the rate of 15 feet per second, because this tip of the ladder is sliding over here as this end of the ladder slides straight down the wall. Okay, so the picture just something, just write down everything you think is relevant. You can always add things later, but I think this is good for now. There's the picture. So step 2, I always think for step 2, okay, what is the rate we know? Okay, what is the rate that we know? Because they're going to typically give us some rate of change. And in this case, it's what we just wrote, right? This is the rate that we know. It says that the ladder is sliding away from the base of the wall at the rate of 15 feet per second. So that's the rate we know. dx dt is 15 feet per second. And then step 3, what is the rate we want? So what is this rate that we want? Okay, so let's see what it says here. How fast is the top of the ladder sliding down the wall when the top of the ladder is 7 feet from the ground? So how fast is this sliding down here? Now this is where when I write these rates down, I want to use the variables of the picture, right? We're going to link this picture into this problem that we're working with. So since I called this y, what I'm really looking for is dy dt, right? Because we want to see how fast is the top of the ladder sliding down the wall when the top of the ladder is 7 feet from the ground. Okay, so if I call this y, then I'm talking about dy dt. Now somebody else could call this h, or you could for height, or you could really call it whatever you want. So if I had called this h, then I'd write dh dt, right? But I happen to label this y. It's up to you. It's kind of an arbitrary thing. You can call it what you want. But since I called it y, then what I'm really talking about here is dy dt. And we're interested in this at the point when y equals 7. Right, so remember this Leibniz notation. This is how we're saying, like, basically y prime at 7, right? So that's the rate we want. Okay, and then step 4, we need to find an equation relating these two variables. Okay, so step 4, find an equation relating whatever's in these, right? X and y. So we want to find equation relating x and y. Remember, to do that, we typically look at the picture and think of the geometry of the picture. Okay, so the geometry in this case, we've got, it's this right triangle. So what you're probably thinking, an equation relating to x and y, it looks like we could use the Pythagorean theorem, right? X squared plus y squared equals 25 squared. So let's try it out. X squared plus y squared equals 25 squared. Now sometimes there's other choices here, but what we want is you want to have these two variables involved and not other variables. So if there's more than one choice, just try to find the choice that just gives you what you want and doesn't require anything else. Okay, so in this case, x squared plus y squared equals 25. And then once we have step 4, step 5 is always the same. We differentiate with respect to t. So differentiate with respect to t. So I look up here and I differentiate these with respect to t. So remember, none of these are t. Also remember, this is just a constant, right? When I take the derivative of 25 squared, I'm just taking the derivative of a constant, so that's just going to be 0. But here, you've got the power rule, so we'll go 2x to the 1, and then this x is not t, right? So then I need dx dt. All right, the chain rule comes in. So we get 2x dx dt plus, same thing with the y, 2y times dy dt equals 0. So step 5, we differentiate. And then, of course, step 6, we substitute known values and solve. Okay, so for step 6, we know dx dt is 15. We know y is 7. We're looking for dy dt. But x, we don't have x in this case. So you look back at our original question, our original picture. Okay, we're looking for x. And we know that y is going to be 7, right? Y is going to be 7. So let me add this in here. So y is going to be 7. We know this is 25. So then we could definitely find x, right? We can use Pythagorean theorem. If this is 25 and this is 7, there will be a value for x we can find. So we could just go over here, kind of off to the side here. We've got x squared plus 7 squared equals 25 squared, right? So x squared plus 49 equals 625. So if you subtract 49 from each side, we get x squared equals 576. And if you take the square root of both sides there, we get x equals 24. Okay, so this is going to be 24. So at the point that is 7, this is always going to be 25, but at that point, this is going to be 24. So now we have everything we need, and now we can plug in these values. So I'm going to go back here and just plug everything in. So x is going to be 24, so we're going to get 2 times 24 times dx dt, which is 15, plus 2 times y, which is 7, dy dt equals 0. So I multiply these together, and I'm going to get 720 plus 14 dy dt equals 0. So that means 14 dy dt equals negative 720, right? And then if I divide both sides by 14, we will get dy dt equals negative 51.4. And of course, we always want the units, but the units are easy because the unit of y over the unit of t, right? So the unit of y, that's in feet. The unit of time is seconds. And notice one thing about this is a negative. This is a derivative. The derivative is negative, which means that y is changing in the negative direction, right? So y is getting smaller. That distance, y, is getting smaller because the ladder is falling. So the negative here means that the ladder is sliding down the wall, right? because y is getting smaller. So the ladder is sliding down the wall at 51.4 feet per second. So when you're answering the questions, if you write out the answer like this, I keep the negative here, right? So I would say dy dt equals negative 51.4 feet per second. But if I use words, I would say something like the ladder is sliding down the wall at 51.4 feet per second. And the word down takes care of the negative, right? It tells us what's happening with that y. That y is getting smaller because the rate of change is negative because the ladder is sliding down the wall. Okay, so hopefully that one makes sense. And of course, as you guys know by now, the way to get better at these is to do more of these. So, lucky for you, we've got some more. So let's take a look at the next one. Okay, example 3 says, how rapidly will the fluid level inside a vertical cylindrical tank drop if we pump the fluid out at a rate of 3,000 liters per minute? Well, step 1, of course, I am going to draw a picture just to kind of get a feel for what we're working with here. So we've got this cylindrical tank, and it talks about a fluid level. So we've got a little level of fluid in here. Okay. And the fluid's coming out of this tank. So you could maybe think of like a little spigot on here or something at the bottom of the tank, and the fluid's draining from the tank. And we've got a height here. I'll just call this h. So the height of the fluid. And okay, I guess it's good enough for the picture. Step 2 says, what is the rate we know? Okay, it says that we pump the fluid out at the rate of 3,000 liters per minute. So if you think of the volume of fluid in here, this would be the change in the volume, right? So it would be like dV dt. And because the volume is decreasing, it's going to be a negative, right? So it's going to be negative 3,000 liters per minute. Right, so the volume of the fluid in here, it's being pumped out at 3,000 liters per minute. So dV dt equals negative. I need the negative because it's going down, right? The volume is decreasing, so the rate of change is negative, right? Negative 3,000 liters per minute. Step 3, what is the rate we want? What are they asking us to find, in other words? They're asking us to find how rapidly the fluid level inside a vertical cylindrical tank will drop. So if this fluid level is h, they're asking us for dH dt, right? dH dt. And it doesn't ask us about any particular time, right? It just says how rapidly will the fluid level drop. And probably the reason for that is because because the radius here is the same, right? It's a cylinder. So this will just drop at a constant rate. So if the fluid's leaking out at 3,000 liters per minute or being pumped out, this will just drop at a constant rate. So they don't really need to ask us at any particular time. dH dt will be the same the entire time. Okay, and then what is step 4? Well, remember, once we have 2 and 3, we need to find a link between these two variables. So we need to find an equation relating blank and blank. Blank is V and H, right? Relating V and H, the volume and the height. And typically to find this equation, we look back at the picture, think of the geometry of the picture. And in this case, probably you're thinking of the volume of a cylinder. So the volume of a cylinder, really all it is, think about a cylinder, isn't it just a circle? Got a circle on the bottom with some height. So the volume is just going to be the area of a circle times height, right? What's the area of a circle? Pi r squared, that'd be the circle. Then you have one more dimension of height. So the volume of a cylinder would be pi r squared h. Okay, so the volume of a cylinder, volume equals pi r squared h. And now there's a couple of things we have to notice here. Okay, the first thing is this radius right here, it's going to be constant, right? So the radius never changes. So we've got a variable here, volume, variable here for height, but pi r squared, this whole piece here is a constant because the radius never changes. If this were another variable and we differentiated, we would need the product rule here, right? We'd have a couple of variables, but in this case, pi r squared is a constant because the radius never changes. But there's something else we're going to have to keep in mind too. So when we find these measurements, we start plugging things in, radius, as far as units go, the radius is going to be meters squared. We're using the metric system because they're talking about liters. So radius squared, the radius would be meters, then we square it, so we get square meters. Then we've got the height would be in meters. So that would give us the volume in cubic meters, right? Because we've got meters squared times meters, so the volume would be in cubic meters. Okay, now they gave us the volume in liters. So we're going to have to just make a little note of this. Sometimes we have to tweak the units a little bit. So the volume is in liters, but the radius and the height are in meters, right? So what we need to know is a conversion. It turns out 1 cubic meter is the same as 1,000 liters. So what we're probably going to want to do, they gave us this in 3,000 liters per minute, but we're going to want to change that to cubic meters per minute, right? Because then these will be, since these are going to be in meters, this will give us cubic meters instead of liters. But that's easy enough, right? If 1 cubic meter is 1,000 liters, then isn't this just the same as saying the rate of 3 cubic meters per minute, right? So let's change this. Let's change this right here to just -3 cubic meters per minute. And then we'll be using the same units for this equation. All right, so that brings us to step 5, where we differentiate both sides of the equation, always with respect to t. Once again, there's no t here, so we're going to use implicit differentiation. Also, this is just a constant. So really all we're going to have here is dv dt equals pi r squared times dh dt. We take the derivative of h with respect to t, it's just dh dt, and this is a constant that just goes along for the ride. And then once we have this, we are finally ready for step 6, where we substitute known values and solve. So let's get a picture here. dv dt is -3, so we substitute known values, so we have -3 equals pi r squared, and then dh dt. So basically, if I want to get dh dt by itself, I divide both sides by pi r squared, right? And that would give us dh dt equals -3 divided by pi r squared. And then the units here, the unit of h is the height, which should be in meters, and time is in minutes. So the answer would be dh dt equals -3 divided by pi r squared meters per minute. Also, notice something else. Since this is negative, that really means that the fluid level will drop at a rate of 3 over pi r squared meters per minute, right? The negative just means height is decreasing. The derivative is negative, so height is decreasing. So the fluid level is dropping at a rate of 3 divided by pi r squared meters per minute. Okay, hopefully you guys are having some fun so far. Are you thinking these don't seem so bad? Hopefully they don't seem terrible, but they They definitely are a little tricky. They're all unique. But we've got one more. This one will get a little more challenging because unlike the last problem, in this case, we're going to have a situation where the radius is going to change. So we're going to have another variable. So this is sort of a classic problem in this section in any calc book in related rates. You'll have this, in this case, underground conical tank. So it's like a cone standing on its vertex, being filled with water at the rate of 18 pi cubic feet per minute. The tank has a height of 30 feet and a radius of 15 feet. And the question is, how fast is the water level rising when the water is 12 feet deep? Okay, so we have to draw this picture first. Conical tank. So it's a cone standing on its vertex. So it'd be like a ice cream cone. And so let's just get a picture of this one and see what it looks like. So we've got something like this. It says that this tank has a height of 30 feet. So it is 30 feet tall. Right, 30 feet. And it's got a radius of 15 feet. So across here is 15 feet. Make this in red so it's a little easier to see. This is 15 feet. And they're talking about a water level. So I put a little water level here. And I should probably put a variable on that, either y or h. Doesn't really matter. I'll just call it h, I guess. We'll say this height is h. All right, so this is our picture. And I guess that's enough for a picture. So once you have a picture, step 2, we want to write down the rate we know. So the rate we know. And let's see, they tell us that this is being filled with water, right? This is being filled with water at the rate of 18 pi cubic feet per minute. So I'll use volume again like last time. dV dt, the volume of water, is equal to 18 pi cubic feet per minute. That's the rate of change that we know. And then step 3, what is the rate we want? What are they asking us for? Well, they are asking us for how fast is the water level rising when the water is 12 feet deep? So this is being filled, so this water level is going up. So they're asking us about how the height is changing, right? The water level. So they're asking us for dh dt at the point where h equals 12 feet. Okay, so we've got the rate. So as you know, for step 4, we're going to have to find some sort of equation that relates these two variables. So step 4 will say, finding the equation relating v and h. Okay, so to do this, again, we look back at the geometry of our situation. We want a formula that has to do with a cone that relates v and h. And there's a formula for the volume of a cone that we've all seen from time to time. You might not remember it, but the volume is 1/3 pi r squared h. So for my class, I'm never going to have you memorize some obscure geometric formulas. So I'll give you the formulas that you need. But in this case, the formula for a cone is this, 1/3 pi r squared h. But there's a problem with this. So if you look at this formula, count the variables we've got. We've got v, r, and h. They're all variables. R is not a constant here, right? R is changing as this goes up. So r is a problem because we don't know about r, and we're not looking for r, right? We know about v, we're looking for h. R isn't part of that. So we don't want it. We don't want to have to use the product rule in here. That would just be a lot of work. If I started taking the derivative of this right side, we've got the product rule. We're going to have an r, a dr dt, a lot of things we don't need. So there's a little note here we need to make sure. So note is this. R and h are both variables. Okay, and we're going to need to get rid of the variable r. Okay, we need to get rid of that one. Because r and h are both variables along with v. V is a variable too, but we want v and h, right? We don't want r. So we want to figure out how to get rid of r. We don't want it and we don't know it. And we're going to be able to do that if we look back to the original picture here. So if you think about this picture right here, and we can use similar triangles here. Right, so if you think of this triangle here in the picture, this triangle is like a big triangle, and then we've got this small triangle. So if you think about these triangles, they're both right angles. They both share this angle, right? This angle here is the same on the little triangle and the big triangle. So they share that angle. They both have a right angle. So what that means is that this upper angle here has to also be the same for both of them. This means that these are similar triangles. And similar triangles have sides that are proportional. So because of that, we could say that 30, this 30 right here, 30 compares to 15 in the same way that h compares to this little r. So I'll just call this r up here. And because these are similar triangles, we can say that 30 compares to 15 in the same way that h compares to r. So if I do this over here on the side here, 30 compares to 15 in the same way that h compares to r, then we could solve this for r. Right, are you convinced? 30, big triangle, compares to 15, big triangle, in the same way that h, small triangle, compares to r, small triangle. So we can take the cross products, right? We can multiply this way and that way. So I could say 30r equals 15h. Then divide each side by 30 and get r equals 15 over 30h, which is the same as 1/2 h, right? Divide each side by 30. So r equals 1/2 h, or in other words, r equals h over 2. And we can use that if r equals h over 2, we can go back in here, wherever there's an r, just put h over 2, right? Because r is just going to be half of h. So then we can tweak this formula a little bit. So we can say v equals 1/3 pi. R squared is really h over 2 squared times h. And then we can just algebraically clean this up a little bit. So we can get v equals 1/3 pi. Well, when you square this, I square both of these, right? So it's h squared over 4. This is h squared over 4 times h. So really, if you multiply all the way across the top here, we're going to get pi h cubed over 12. Or in other words, volume equals pi over 12 h cubed. Right, so we've got, let me clean up that 12 a little bit here. Okay, there we go. Pi over 12 h cubed. So we've got a volume formula here, but we've got a better one here because this one only has two variables, v and h, and that's what we want, right? V and h. We want an equation relating v and h. We don't want extra variables in here. And in this case, we were able to clean it up because of the geometry of our situation. So now we've got what we want, equation relating v and h. Okay, so now we are ready for step 5, where, of course, we differentiate with respect to t. So it'll give us dv dt equals, okay, we've got the power rule here, right? 3 comes down, so it's 3 times pi over 12, or 3 pi over 12 h squared times dh dt. So of course that is dv dt. We can cancel and get pi over 4 h squared dh dt. Okay, and then step 6, I'll put up here, substitute known values and solve. Okay, so let's see. dv dt is 18 pi, right? Let's look back at our big picture here. Okay, so we're going to substitute known values. So dv dt is 18 pi. So I can write this over here. 18 pi equals pi over 4. You've got h squared. Well, h is 12, right? So h squared is going to be 144. And then dh dt. Okay. So let's see, if we clean this up, 144 divided by 4 is 36. So we end up with, let's see, 18 pi equals 36 pi dh dt. So if I divide each side by 36 pi, I get dh dt equals 1/2, right? Divide each side here by 36 pi. 18 pi over 36 pi is just 1/2. And then I want to put the units in here. This is the unit of height over the unit of time, right? Height over time. H was this height here. So that was in feet. So we get 1/2 feet per minute. That's the unit of measure for dh dt. So that means that the water level is rising by 1/2 foot per minute when the water is 12 feet deep. Now I know what you're probably thinking, down to the last problem, and you haven't seen any trigonometry yet. And I know you guys get very excited if I don't do at least one trig problem a day. So here is your chance. There'll be a little bit of trig in this one. And this one involves a rocket rising vertically at the rate of 5,400 miles per hour. Pretty quick, right? Pretty fast. But if you want to escape Earth's velocity, or if you want to escape the Earth's gravity, the escape velocity from Earth is about 25,000 miles per hour. So it's fast, but you're still going to be stuck on Earth, right? If you hit that mark, about 25,000 miles per hour, about 7 miles per second, at that point you can shut the engine off and gravity won't be able to pull your craft back. If you don't hit that mark, you're going to have to have the gas on, so to say, the entire trip, which would not get you very far. So you have to hit that escape velocity to actually escape from the pull of gravity from Earth. But anyway, it's still pretty fast. This rocket is rising vertically at 5,400 miles per hour. Got an observer on the ground standing 20 miles from the rocket's launch point. And the question is, how fast in radians per second is the angle of elevation between the ground and the observer's line of sight of the rocket increasing when the rocket is at an elevation of 40 miles? Okay, so step 1. You should do this on your own and see if you can do it. This one's a little tricky, but we've got a few of them under our belt now. So why don't you see if you can set up step 1 to get a picture of this one. All right, so this is what I've got. Got a picture here, and you got 20 miles here, right? You got the height here, so the rocket would be right here. There's the rocket. We also know this h is increasing, right? So if I call this h, then we know that dh dt is 5,400 miles per hour, right? So that's the rate we know. Dh dt equals 5,400 miles per hour. Okay, so then Step 3, the rate we want. All right, so it says, how fast in radians per second is the angle of elevation between the ground and the observer's line of sight of the rocket increasing when the rocket is an elevation of 40 miles? Okay, so basically now we're talking about this angle theta, right? So we want d theta dt at the point where h equals 40. They may have also noticed something. We're going to have some problems with the units here because they're talking about radians per second, and this is miles per hour. So we're going to have to do something with that. So we should probably just go ahead and get that set up right now. So we've got 5,400 miles per hour. They want radians per second. So we want miles in terms of miles per hour, but we want to change that to seconds because we've got radians per second. So we need to do a quick conversion here. So we've got 5,400 miles per hour. And let's change that to miles per second, right? Because we got radians per second. So we're going to need to change this to seconds. So we can do a conversion here, right? So we know that 1 hour is 3,600 seconds, right? Because there's 60 seconds in a minute, 60 minutes in an hour. So 60 times 60 is 3,600. And then if we multiply straight across, so just, you did unit conversions in algebra class, right? So multiplying by 1, because 1 hour is the same as 3,600 seconds. But this would allow us to cancel the hours. And when we multiply straight across here, we get 5,400 over 3,600, which is actually reduces to 3 over 2. And the units we're left with is miles per second. So we get 3/2 miles per second, or in other words, 1.5 miles per second. So let's change this dH dt. We'll change that to 3/2 miles per second. So 1.5 miles per second. Pretty fast, right? But okay, so that way the units are good. Which brings us to step 4. We want to find an equation relating h and theta, right? H and theta having to do with this. So since theta is involved, we're probably going to need a trig function. So think of it like this. You want a trig function where h is involved and probably 20 is involved because we know 20. We don't know this distance here, this hypotenuse. We don't know it, and we're not looking for it. So we're not going to want a trig function with this. So what trig function could we use here? Remember, so trig functions are ratio of two sides, right? SOHCAHTOA. Remember, it's a little acronym most people use. So we want an angle. We want a trig function using this angle and these two sides, right? Again, we don't want this side because we're not looking for it and we don't know about it. We're interested in this side and we know about this side. So probably you're thinking tangent, right? Probably thinking tangent. So we could say, okay, we've got an equation here. Tangent of theta equals h over 20, right? Because tangent of theta, tangent is opposite over adjacent. So tangent theta equals h over 20. And then step 5, we differentiate with respect to t. All right, derivative of tangent theta is secant squared theta, right? So we will get secant squared theta d theta dt, right? Remember, we're differentiating with respect to t, and there is no t here. This is theta. So we're going to use implicit differentiation. So derivative of tangent theta, secant squared theta, but this theta is not t, so then we need d theta dt. And that equals, and remember this is really, this h over 20 is 1/20th h, right? So if you think of it like that, the 1/20th is just a constant, so you go 1/20th dh dt. Okay, which leaves us with step 6, which is substitute known values and solve. All right, sometimes this pen has a mind of its own. Substitute known values and solve. Okay, so secant squared theta. Well, we're going to have to look at our picture here. And I'm just going to redraw this so we can see it over here. Okay, just a straight line here. Here's theta. We know this is 20, right? And we want this rate of change at the point where h equals 40. So this height is going to be 40. So if we're going to need to find secant, well, I never find secant. I just find cosine. Remember the reciprocal function? I just find cosine and then flip it. So SOHCAHTOA, right? So typically you don't learn secant, cosecant, and cotangent. You just use the reciprocal function. So if you remember, every cofunction or every function is paired with a cofunction as its reciprocal. So secant, its reciprocal is cosine. So I'm going to look at this and just find cosine squared and then flip it. So to do that, I'm going to need to know this, right? But we can use Pythagorean theorem because 20 squared plus 40 squared equals this squared, right? So if you do some math there, you'll end up with 20 squared, which is 400, 40 squared, which is 1600, and you add those together and you'll get the square root. Well, you get 2,000, but then we have to take the square root, right? So this squared plus this squared equals this squared. But I'm not going to take the square root of it because we're going to have secant squared anyway, right? So if I plug this in, so cosine of theta is adjacent over hypotenuse. So cosine theta is 20 over the square root of 2,000. Right, which means that secant theta is just the reciprocal of that, but we need to square it. So if I find cosine squared and then flip it, cosine squared is 400 over 2,000, right? Because I square these, 400 over 2,000, and I flip it so I get 2,000 over 400. So secant squared is 2,000 over 400. Times d theta dt, which is what we're looking for, times d theta dt equals 1 over 20, and then dh dt, and we know dh dt, right? dh dt is 3 halves, so this is times 3 halves. So then we just do a little algebra here. If I want to get rid of this thing, I could multiply by the reciprocal. So basically we'll get d theta dt is equal to 1/20 times 3 halves times 400 over 2,000. And then we can clean this all up. So we get a lot of canceling here, right? So this is really that goes. So really 4 over 20 is really 1/5, right? So this is really just 1/5. So if you multiply straight across, we're going to get 1 times 3 times 1, which is 3 on top. 20 times 2, which is 40. 40 times 5, which is 200. So we really are going to get d theta dt equals 3 over 200. Or if you prefer, 0.015. And then the units are going to be radians per second because it's a unit of theta, which is radians, and time, which is in seconds. All right, so that gives us quite a few examples. This now is time for you to try some of these out and try the homework problems. Just be aware this section, as I said, it's a challenging section. It should take a little more time than usual. So make sure to give these a try. The 6 steps that we've been going over will be sort of a guide as you work on these. Just be aware there will be some challenges, so give them a try and let me know if you have any questions.